like to introduce Konstantinos Kolias. Kostas Kolias joined the computer science department at the University of Idaho in 2018. His main research interest involves security and privacy for the Internet of Things and for critical infrastructures. He's also active in the design of intelligent intrusion detection systems with a special interest in side-channel-based IDS. Other areas of interest include mobile and wireless communication security. And with that, I will turn it over to Kostas.
Hello, everybody. Thank you very much for accepting my paper, and here I am. I hope everybody can hear me. And today we are going to talk about how it is possible to use EM, electromagnetic-based fingerprinting of digital devices, hardware components, in order to authenticate devices inside the network. So what is the problem? Modern computer networks, including critical infrastructures, consist of myriad of digital devices, and generally in highly secure networks, there is an effort to put to restrict the devices to domestic manufacturers only. However, in reality, each device is a host of countless microscopic components produced by various vendors from all around the world, some of which are not even benign. So some of these vendors may inject malicious components even at the hardware level that may somehow compromise the device. The worst thing is that such actions of the attacker may get lost across the complex relationships formed in the supply chain. So actually an attacker has the capability of acting virtually undetected at any step of the supply chain life cycle, including during the design phase or the manufacturing phase, during the transferring of components or the entire device to the end user, during the operational phase, during even the retirement phase where the device gets normally recycled. In this work, we will focus primarily on the operational phase, where the device has already been deployed inside the network. And generally, this is considered the longest phase in the supply chain. More specifically, let us consider the following example. A network relies completely or partially on third-party vendor for the maintenance or repair process of its devices. However, at some point in that process, a malicious employee can substitute a device with its malicious clone. As the majority of the supply chain's attacks are applied at the hardware level, malicious activity has higher chances of going unnoticed, completely unnoticed. Generally, the users have some sort of inherent trust on the hardware, and sometimes users perceive hardware, some unusual behavior, not a product of the hardware, but rather a malicious software being installed. Software updates will not solve such problems, such malicious operations of injections of fake devices, and complex processes may be required not only to remedy such unwanted behavior, but also even to identify a malicious modification. The easiest solution, of course, is to revoke such devices completely, remove them from the network, but in some cases, this is not a viable solution, especially if such attacks, such malicious attempts are done at massive scale. From the adversarial point of view, such attacks seem lucrative because the aggressor may achieve leakage of private information, remote persistent access to a system, and even through that system, through that device, the entire network, or even complete system failure, for example, denial of service attack against that component. Again, all this can be done in a relatively stealthy fashion. Why? Because generally hardware enjoys almost complete trust from the user. So we propose the development of a low-cost authentication system to be deployed. We envision that this system could be deployed as an authentication kiosk that may be placed at the entry point of the network, or alternatively at as a pistol, authentication pistol that is used during routine checks in the network. The system performs authentication at the hardware level to provide protection against malicious substitutions of devices. That is basically the main purpose of the system. We assume that at an initial phase, all the devices inside our network have been fingerprinted, have gone through a process of analysis of basically identified what we have and what is what. During this phase, we assume that these devices are benign and that they are not shipped bearing any malicious components. In a sense, this is a strong assumption, but our system makes that assumption. Therefore, we can say that the proposed system focuses on solely the maintenance phase of the supply chain lifecycle. So this concept is based, the entire system is based primarily on two observations. A, the analog signals get emitted from the CPU and other components of the digital device in an involuntary way during their normal operation. These signals correspond to instructions that are executed inside the CPU, which may consume slightly different amounts of current for their execution. And the second observation is that due to the imprecise manufacturing processes, each device bears minimally distinct hardware variations. That is true even if we examine devices of the same manufacturer, the same model, produced from the same factory. For this reason, the electromagnetic signals get modulated in a very distinct way. Despite looking generally similar, one may examine these signals closely, and they will observe very characteristic signatures that are indicative of a device, that particular device, and no other. In this image, you can actually you can observe signals emitted from the CPU of 4 different devices of the same manufacturer running the exact same operations at the exact same with the exact same sequence. The signals look very similar, although if we notice closely, you will be able to identify very small differences between the same set of instructions corresponding to device A versus device B. Before we move on, let us remind you that our approach falls under a greater research umbrella of side channel analysis methods. Traditionally, side channels have been exploited for offensive purposes, that is, to derive secret keys. Side channel analysis methods have also been applied for failure prediction. For example, in the past, researchers have analyzed acoustic signals to infer the quality and quantify, basically, the level of natural degradation of analog components inside factories, whether they are about to fail or whether they are doing their operation normally. Regarding the detection of hardware trojans, the most important techniques rely on X-ray analysis or some destructive methods that can only be applied at a very small number of components. Electromagnetic analysis and power consumption analysis, or magnetic analysis, have been proposed and applied for identification purposes, but most of the proposed approaches rely on the installation of software inside the devices, and basically other sets of approaches rely on very expensive equipment in order to capture or analyze the signals. So basically, the proposed system architecture is comprised of two phases: training phase and testing phase. And that at the training phase, we attempt to fingerprint the devices by taking advantage of a database of collected electromagnetic signals that were basically manually collected through some sort of antenna that we will examine in the process, and basically stored at any commodity type of database. The training phase is comprised of two stages. One is the creation of a baseline of all benign devices, and that is their signals, the electromagnetic emanations. And this step is done using the local outlier factor. It is an outlier detection algorithm, and it will be examined in the process. And the second stage is creating a model for distinguishing between each one of the devices. And this step is done, relies on k-nearest neighbor algorithm, which is very basic, and hopefully most of the people in the audience should know the basic principle. During the deployment stage, new signals arrive. We have not seen these signals before. We wish to know whether they look similar to the benign signals and of a particular device, or they are totally unknown to us, therefore most probably correspond to a malicious clone, a malicious device. During the deployment phase, these newly arrived signals get compared to the baseline so that we provide authentication whether the device is malicious or not. And at the second step, they are compared against the k-nearest neighbor model created previously in order to provide device of identification. K-nearest neighbor is a well-known classifier. It is a supervised machine learning method that requires labels for both normal and potentially abnormal instances. And that is basically the catch, that is the drawback of this particular algorithm. We cannot know in advance all potential, the signatures of all potential anomalous or malicious components that may be introduced into our network. So therefore, we have to rely on an unsupervised algorithm to provide this first step of normal/benign versus unseen/anomalous. And to deal with this inefficiency, like we mentioned earlier, we relied on the local outlier factor, which is an unsupervised learning method. And let us briefly describe LOF. Basically, LOF is an outlier detection technique, and at its core, very similar to KNN, relies on distance-based metrics such as the Euclidean distance to infer the level of the similarity between signals. More specifically, the algorithm identifies the observations that are significantly different than others by automatically forming clusters and calculating their density. Similar signals that correspond to the same device tend to gather in the same cluster, while outliers that most probably correspond to an unseen device are basically isolated. In this picture, the isolated outliers, signals that most probably correspond to never seen before hardware are indicated in red. So we relied on inexpensive off-the-shelf components, including an electromagnetic probe that was placed on top of the CPU of an Arduino device, a signal amplifier to make our simple signals clear, and an oscilloscope to store the signals on the disk. We conducted 2 rounds of experiments. For the first round, we relied on a set of devices of the same model, which were produced by different manufacturers. So all of these models were Arduino Mega, but they were produced by different vendors. And on the second round of experiment, we relied on a set of the same model and same manufacturer devices. At this point, we have to make clear that we basically did 2 basic assumptions. During the fingerprinting step, we assumed that all devices are benign. That was mentioned before, and this is, in a sense, is somehow a strong assumption because, like we mentioned earlier, the attacker may have chances of doing bad things, injecting their malicious components inside the devices before they are even shipped into our network. The second assumption we made is that if we are able to distinguish between devices bearing such level of similarity, then most probably we should be able to distinguish devices that are new, different, and bear some sort of extra malicious component or some sort of altered hardware component. We collected, for our experiments, we collected 10,000 samples from 4 different devices for each round of the 2 experiments that we did. We proceeded into 10 rounds of evaluation in which 1,000 samples per device were used. So some sort of modified 10-fold cross-validation. But in our cases, we assumed that 3 of these devices were benign and the 4th was malicious. In reality, the malicious one did not include any hardware, extra hardware or hardware Trojans. We simply said that it was just a malicious clone. For the training step, we just retained 20 signals, 20 samples for each one of the 3 benign devices, while for the testing phase, we used the rest of the 980 signals per device, and also included the 4th, the extra unseen/malicious device. So we relied on metrics such as accuracy, F1 score, and area under the curve to identify, to evaluate whether our system would be able to provide first level of authentication and a second level of identification. From our experiments, you can see the first round of experiments where we had devices from different manufacturers. We were in a satisfactory way able to distinguish between normal devices that were fingerprinted, the 9 devices that were part of our network, versus the new device with an average accuracy of 97.9%. And actually, when I say accuracy, I refer to F1 score, because in this case, our data set is unbalanced. You will see that we have many more benign signals rather than the malicious signals. Therefore, we rely on a metric which is optimized for unbalanced datasets, which is the F1 score, and it provided a very good, very satisfactory predictive accuracy of around 98%. For the other round of experiments, the accuracy, when we had the same device from the same manufacturer, the accuracy was 99.4%. And that was only for the authentication part. After that part, we proceed to the second round, the second stage of identification, where the signals get passed and are tried to basically get mapped to one of existing fingerprinted devices. And for this stage, either for the first round or the second round of experiments, our accuracy was perfect. So basically, the proposed solution, hopefully with this work, we provide the first experimental evidence that proves that it is, in a sense, possible to provide device authentication and identification, and in order to protect against malicious substitutions of at the hardware level. The advantages of our approach over similar approaches are that, one, it is totally external. It is not destructive in any way. It provides authentication to digital devices that may bear some minimal variations at the hardware level. It does not require any software to conduct the analysis. And for the same reason, it can also support legacy devices. And unlike other approaches in this field, it relies on completely off-the-shelf, inexpensive equipment. Moreover, the fingerprinting phase can be done once, and that's it. And you can consider that in secure infrastructures, this phase most probably is conducted either way. So it adds very little burden to the entire introduction of network components inside the secure network. So basically, we believe that the proposed system is a valuable mechanism for detecting and discarding, if necessary, malicious components from the network. And it may significantly contribute to the overall network resilience. And as a future directions, we plan to explore the possibility of relying on directional and high gain antennas in order to achieve the same detection accuracy from a greater distance. And also, we would like our next experiment to be conducted upon a greater set of devices, including PLCs, which are dominant components of most modern critical infrastructures. And with that, I would like to take your questions.
Great. Thank you. We do have a few questions in the chat window. We'll try to get to most of them. The first one, as you mentioned, you want to move towards high gain antennas. Have you had trouble with electromagnetic background noise, and have you done these experiments in an anechoic, an EM anechoic chamber?
Yeah. So basically, with the described experiment, we relied on an electromagnetic probe that was basically placed on top of the CPU, so 0 distance away from the source of the signals, and all are noise-free, in a sense, virtually noise-free. We didn't have any interference, and we didn't have any significant environmental noise, and it didn't impact. I assume that the very small loss in accuracy that we previously discussed was due to very subtle noise or interference from the environment. We conducted preliminary experiments with other types of antennas placed on greater distance. The noise levels were significant, and it dramatically impacted the accuracy of the system. So, for example, with an Aroni antenna that was placed 6 inches away from the CPU, the accuracy dropped to around 70%, the authentication accuracy that is, while when that antenna was placed at around 18 inches away from the CPU, the accuracy dropped at 50%, which is basically a random coin toss. The experiment was the accuracy. Basically, the system is useless. However, we were able to test and apply several types of denoising techniques, and we saw that SVD-based denoising was very effective, and it boosted the accuracy all the way back to 99% again. So at this point, again, we talking about preliminary experiments, we can say that it is possible, even from a distance of 18 inches away from the CPU, to reliably do authentication, EM-based authentication.
Okay, so let me follow that with one clarifying question here. That what you're trying to detect is a change in hardware or new devices or new behavior, not necessarily judging if it's malicious or benign, but that it's something as anomalous. Is that right?
Yes, that is correct. Unseen devices. We assume that if we have an authentication kiosk where only fingerprinted devices are allowed to pass through that entry point of the network, inside the network, we assume that anything new, non-fingerprinted in an environment, a secure environment, most probably should be something malicious or something that at least should be reported and or removed.
Okay, great. And have you considered the changing signatures of hardware caused by aging effects or other interference from neighboring devices?
That is an excellent question. And when I was conducting this research, I actually thought that this should be very minimal. However, from further research that I did after this paper was published, I realized that the influence of natural degradation due to age, basically, it is a factor that may significantly impact the behavior and the accuracy of the system. So that is something that we have not examined, and most probably it's something, a very good future direction for this project.
Okay, and I think related to that future direction, have you considered a malicious device, a cleverly designed malicious device that would copy and emit a similar signal to a benign trusted device?
So here's the thing. Yeah, here's the thing. A lot of people think that may assume that this is very easy. However, take into account what we are talking about is basically a replay attack, right? So instead of having the original device, we introduced a malicious clone. That malicious clone is basically off at this point. However, we have another antenna, we have another some sort of transmitter embedded in that device, but the only thing it does during the authentication step is basically replace the benign signals from a benign device. Well, this will not work because the transmitter itself has also a very characteristic signature, let's call it like that, hardware morphological characteristics that may impact in a way the specific signals that are transmitted. And for this reason, these signals, even though the attacker would intend to transmit these signals, most probably the signals would be modulated in a way, they would be transformed in a way that are not 100% the same as the intended ones, the signals that the attacker would like to transmit. Of course, a lot of things can be done towards this direction, and more sophisticated approaches could potentially be adopted by the attacker, so that basically circumvents this hardware characteristics of the transmitter and somehow modulate the signal to look exactly the same as the intended ones, the ones that correspond to a benign device. I believe this is generally should be hard, but it's another interesting direction for the project.
And I think we just had one other comment that I don't want to miss, and then we'll move on. I think a comment more than a question, but if an attacker had some code laying in wait that was not active until a particular external event triggered it, you may not be able to discover that within the hardware if there was some dormant hardware.
Yes. Yes and no, in a sense. So we are talking about modification of an existing device. If we are talking about the introduction of a new device, which is basically exactly the same as the same model, the same characteristics as a benign one, but with the injection of a hardware Trojan or some other modification that might be triggered under specific circumstances. For the second case, we should be able to identify, because the CPU basically should be different, or the other components of the hardware should be different, and therefore the signals should be different. Remember, we are not necessarily talking about, at this point, talking about software modifications. For the scenario where we are talking about a malicious modification of a benign hardware, most probably the modification would go unnoticed, unless we have that particular event that would trigger something, an additional, basically functionality operation.
Great. Well, a very interesting presentation. Thank you very much, Foster.